Okay, so let's go to the rate. So it's problem 5, right?
Yeah, and it's,
okay, so just go ahead and read
based on your answers from number 1, what's the average metabolic energy consumption rate of the average human?
Oh, sure.
Expressed in watts and hours.
Oh, perfect.
I found that 1 watt is equal to 1 joule. Well, 1 joule is equal to 1 watt per second.
Almost. You didn't quite say that right.
1 watt is equal to 1 joule per second.
That's right.
You're totally right. You have it.
Yeah.
I had that mixed up. No wonder I was having problems.
Yeah. Okay, so this is a perfect time then to review energy versus power. So I'll do it a few different ways. We did this on the first day or 2 of class, but it's a good time to do it again. So I'll just write it mathematically, and then we'll look at it graphically, and then I'll also give you an analogy. There's 3 different ways to look at it. So we know that power equals energy divided by time. Another way to write that is energy equals power times time. Philosophically, time is almost always on the right-hand side of the equation. If we were doing relativistic physics in here and plotting the storyboard for the movie Interstellar, where he comes back and he's older than his daughter's older than he is, time would be on both sides of the equation. Time would be this relative thing. Where we are right now, time is just sort of ticking away, and it's on the right-hand side of the equation. You really can't do much about it. So in general, in equations, this is the independent variable, and this is the dependent variable, right? And when we plot those things, we'll do it like this. This is time here. This is energy here. This curve is your power curve. It's how quickly you're consuming energy. Because it says so right there. Power equals energy divided by time. So power also equals some change in energy over some change in time. What's that look like? Well, on the graph, I've drawn this curve kind of boringly, but on the graph, here's a little delta E. And what is this delta E? Well, the delta E could be how quickly chemical energy is flowing through your body and turning into kinetic energy as you run. It could be how quickly chemical energy is flowing through your body on a cold day to keep you warm. It's a change. It's the energy changing from one form to another. So that's your delta E right there between those 2 little chunks. And what's this? Well, that's the delta T. That's the change in time. That's how long it took you to digest your lunch or run a marathon or what have you. So that's the definition of power. Power is the change in energy over the change in time. So that slope, so something that's happening very quickly. So here's your Usain Bolt, your Lance Armstrong, etc. Here's your couch potato down here. All right, so let me draw that one more time. So let's just say this is your sleeping curve. This is your running curve, and this is just sort of whatever, walking around, sitting in class. So that's how to look at this graphically. So again, there's energy, there's time, and that's just basic metabolics. So mathematically, 1 joule equals 1 watt second. 1 watt times 1 second. So 1 joule equals 1 watt second. 1 watt equals 1 joule per 1 second. Another way to write that is just joules per second. And we saw that. We saw it with the dimensions. So time is a dimension, energy is a dimension, power is a dimension, and now we've shown it in units. What's another unit for power besides the watt? Because we talked about a lot, there's a lot of different units we use for energy, calories, BTUs, therms, kilowatt hours, megajoules. What's another unit for?
Horsepower?
Yeah, horsepower. And what's the conversion between watts and horsepower?
746.
How many? I think it's 746.
746?
I think so.
I think
747?
747. 745.7.
745.7, so 746. Okay, so 1 horsepower equals 1 horsepower, meaning you can write it either way, equals 1 horsepower. I don't care how you write it. Equals, let's just stick with the 3 significant digits. So is it 745.7?
Yeah.
Yes.
Okay, so that's just going to become 746 watts. So now we understand the relationship between power, energy, and time. We know that we now know how to manipulate the units among power, energy, and time, joules, seconds, and watts. And we also know that power can be measured in horsepower or watts, and there's the conversion. So the conversions work the same way they did with the energy. But let's first, well, I'm going to do one more thing. With the power and the energy. So I've got a Prius up here, and I've got a dragster down here, and I'm going to give them both, gosh, let's just give them both 1 gallon of fuel. How far is the Prius going to go?
About 60 miles.
Yeah, 50 to 60 miles. How far is the dragster going to go?
It won't even start.
It won't even start. It's gonna sit there and maybe spin the. It's gonna evaporate, just being poured into the tank, right?
Like 3 miles long.
You know.
Right, a couple hundred yards.
It might make it. It might make it. Let's just say 100 yards, just for the sake of argument. Maybe if it's lucky. 100 yards.
Or right into the carburetor.
Yeah, 100 yards. So my point here, what among power, energy, and time, those are the only 3 things you get, power, energy, and time, what is this most analogous to, the 1 gallon?
Energy.
It's energy. It's how much energy you started with. How fast is the Prius going to go?
30 miles.
Yeah, 30 to, let's just say 30 mph. And let's just say the dragster, for the sake of argument, I know it's not going to go from 0 to 60 in 100 yards maybe. But let's just say it's doing 200 miles per hour, for the sake of argument, at some point during its travel. What is this? Is this power, energy, or time?
Time.
That's power.
Yeah.
Yeah, that's power.
Distance.
Yeah, and in a way, the distance is a little bit like time. The dragster's still here. You burned up all your fuel, so you never made it to the picnic on time. You burned through all your fuel. Yeah. So that's another way to think about it. Is energy could also be the distance in this case. You could also think of this as you could also think of this as energy. But absolutely, this is velocity is analogous to power because it's distance per time. Distance per time. So that's absolutely the way to think about power.
Is there a formula for that too? Is like power equals distance times time? Is that what it is?
No, the equation here is velocity equals distance over time.
Okay.
Distance equals velocity times time.
Okay.
So very similar equation to energy equals power times time. Yeah, so very analogous. Yep. Good question. Okay, so to finally answer the question, what is one human power? So let's just start with the well, I'm going to make it easy and just start with 10 megajoules per day. It's kind of easy. 10.
That's a technological consumption rate?
Nice and easy.
Is that what you're thinking?
Beg your pardon?
The technological consumption?
This is the metabolic.
Okay.
Technological is 200 megajoules per day
Mhm.
on average. Yeah. So 200 megajoules per day. Let's just turn that into watts. So one day,
Kilowatts.
watts, kilowatts, megawatts, gigawatts, turn whatever we want to. But one day equals 24 hours. Right? But, gosh, I'm looking up here, an hour is not the unit we want. We need seconds, equals 24 hours. And then, I love,
600 or something?
yeah, I love to just do it like, yeah, let's just hop right to seconds. So, again, 1 hour, I'm going to multiply by 1 again. 1 hour is, in fact, 3,600 seconds. I don't know why I made that thing so long. Better erase it. This is how I like to write the multiplication. You know, you can put a dot in there, you can put parentheses, but like, it just looks simpler and cleaner this way. It's still multiplication.
Mhm. It helps you kind of
There's
like
Organize.
keep in your mind the cross
Yeah.
multiplier, like the cross canceling, you know?
Yeah. It's just simple. It's just easy. Okay, so let's run that. And I'm gonna treat. And remember, we were talking about arithmetic and powers of 10. I'm just going to treat 24 and 3,600 like the arithmetic, and ignore the powers of 10. They come along for the ride, as you well know. So 24 times 3,600 equals 86,400 equals 86,400 seconds. 1 day equals 86,400 seconds. Yeah. And if I ask you this, what does 1 day divided by 86,400 seconds equal?
1.
You would tell me it equals 1. Yeah. Okay. So I can multiply this thing, or maybe I'll multiply this thing, 86,400 seconds per day. Actually, no, I want the first one. Yeah. So I'm going to multiply this by 1. 1 day divided by 400.
And then you can just convert the megajoules to joules?
I could.
Is that what you're going to do?
We'll see. Let's just see what happens.
Okay, I'll see what happens.
We'll see what happens. There's all kinds of fun ways to do it. And on this calculator. So, gosh, I think there's a button on here just to flip that. So I want that in the denominator. There it is. So it's just 1 over x times 10. So 1.56, again, I'm just going to use 3 significant digits. 1.56 times 10 to the minus 4th. Oh my gosh, what is that thing?
Why can't it be 1.5 if it is 1.157? So it would have to be 1.26?
Let's just see it.
I'd have to look back at that.
Yeah, let me get back to it. 1.5, well, there's a, oh, I'm sorry, I skipped a 1. So 1.157, yeah, there we go. Let's just write it that way.
1.16 then if you wanted to?
Yeah, 1.16.
Okay.
1.16 times 10 to the minus 3rd. And that's megajoules per second. Now, there was a suggestion maybe I should have turned this into kilowatts or kilojoules first.
I thought we were trying to get to watts and horsepower.
We are.
So-
And really, we're actually there because we're actually at megawatts right now.
Mhm.
So we can hop up and just say this equals.
I guess that's true, yeah.
Just make sure I did this
I
right.
think that's the funny thing about math is there's so many ways to get to your destination, you know?
Yeah.
There they are.
Let me make sure I did that right. I'll make sure I get all the numbers in there correctly. 10 divided by 86,400. Let's do that one more time. 10 divided by 86. Yeah, 1.15 times 10 to the minus 4. Yeah, that's where the error is. So that's 1.16 times 10 to the minus 4. Yeah, just always double check. Minus 4 megajoules per second. Now, to get to kilojoules, I know that there are 1,000 kilojoules per 1 megajoule. So I can now multiply this by 1 megajoule. And here is 1,000 kilojoules. Sorry about that. Now we can put all of our problem-solving skills to work here. This is your arithmetic, right there. So 1.16 times 1 is 1.16. Here are your powers of 10. 10 to the minus 4th times 1,000 is 10 to the minus 1. That's the best way to write that. A little bit clunky, but times 10 to the minus 1. And now we'll take care of the units. Megajoules are gone, and I've got kilojoules per second. Well, I also know that 1,000 joules is the same as 1 kilojoule, so I can just kind of keep doing this all day long. So 1.16 times 10 to the minus 1 kilojoules per second times, I'm going to use parens here, this is getting a little bit, let's put this whole thing in parens, a little easier to see, times 1,000 joules per 1 kilojoule. Again, 1 times 1.16 equals. Now, I'm actually gonna run this number so I'm not continuing to use scientific notation because, frankly, it's just getting clunky at this point. Let's go back to the calculator. And I'll take 1.16. Yeah, let's do it this way. Not sure this guy actually has scientific notation on it. Scientific. Let's see here. 10x. Just do 1.
Let's see if that's part of the option.
10x equals 10. So let's do. Oh, there's an exponent right there. Yeah, thanks. 1.16. There we go. 1 plus minus. There we go. Times, yeah, so it just went ahead and did that little conversion for me. Times 1,000 equals 116. So I just did, 1.16 times 10 to the minus 1. We know that is 0.116 times 1,000 is 116.
So it's
Joules.
116, yes. Joules per second. Oops. Equals 116 watts. That's, so there it is there's in watt. That's one human power. Sounds very powerful. It's pretty amazing though. I mean that we do as much as we do with just that much pretty efficient machines we are. Now, if I'm, climbing a mountain or wrestling a grizzly bear or whatever you do out here in Montana, you're gonna be triple, quadruple that.
You're gonna need that much more.
Yeah, but
Another 8 in here.
and believe it or not, you go and look at Olympic weightlifter throwing 400 or 500 pounds over his or her head. I mean, they're well over a horsepower for half a second. So it's possible, but not that repeatable. Now, the only thing we have left to do here is to convert that to horsepower. So
It's like we go from being a Prius to a dragster.
yeah, we have different gears. 116 watts, and I'm going to multiply that. What did we say? 7.
It's 745.7, so it's
746 watts is 1 horsepower. So divided by 746 equals 0.115. Or 155. Just trying to get a little bit of number dyslexia here. So I've used 3 significant digits there and drag it out because, 3 is plenty. 3 is almost always the perfect number for these type of problems. If you wrote 1.6, it's fine too. Or sorry, 0.16. That's also fine. All right, and that's that. I mean, really, what I did there, it's the same exercise repeated over and over for whatever units you're using. So I think what we've done are units conversion between different types of energy. That was what we did first. I also used a currency analogy, dollars and cents. We converted the word problem into an algebraic problem, boil it down to really just an arithmetic problem. We re-examine the relationship between power, energy, and time. Fundamental. And I guarantee you, now that you know this, you'll see this error made all the time. If somebody, oh, this thing burns 100 megawatts a day. Well, no, it's running at 100 megawatts, 24/7, 365. You'll sort of say, oh, Colstrip burns 2 gigawatts a day. Well, no, if it's running at
Yeah.
2 gigawatts, you multiply those 2 billion joules per second by the seconds in the day, and that will tell you how many joules of coal.
Yeah, they're just
They burn.
using the wrong unit measurement to
Did we do
express it.
Did we do the coal problem in this class? We didn't.
Uh,
We didn't do it. Did we do it?
I don't know, but we did do something similar where you made like the point that there's a really big difference between energy and power.
No, yeah,
It's wrong.
we solved the problem in another course, and at the rate of current fuel consumption, coal is being burned at the rate of one coal car traveling at 180 miles per hour. So think of it this way: every 5 minutes, a coal car disappears into Colstrip. Every 5 minutes. That's how fast it burns it. Is that fast? Is it slow? Well, that's how fast it is. Now, if you added up all of so just imagine, a coal train going slow enough that it takes 5 minutes for that car to enter the plant. If you did that for all of the coal plants on the planet, it's the same as a single. So just imagine all of the coal plants just being in one place. Instead of all over the planet, they're all in one place, and you only have one coal train. It's doing $1.80.
I'd have to go 180 miles an hour.
That's the
That's
current.
the rate
That is the
that
current.
it's burning.
That is the current rate of consumption. We are driving
Wow.
one train into one plant at 180 miles an hour.
Blast.
Yeah.
My
Yeah.
God.
All right, thanks for clarifying.
Sure.
Appreciate that.
Yeah.